Hello everyone, I'm going to introduce the kinetics of methane production in batch digesters. We talked about the BMP before, or methane potential, how we can do experiment to uh, calculate the BMP. And today we are going to introduce common models to predict the methane production. So kinetic models are empirical models, means that they can depend on experimental data. And studying this kinetics for methane production from different feedstocks is important when designing and evaluating digesters. For example, if you are trying to compare different temperature, you need actually to calculate the methane production kinetics in terms of rates, or maybe lag phase, or maybe the maximum methane potential, or the maximum amount of methane that you can uh, obtain from certain biomass material under certain conditions. Usually, first order models are commonly applied to describe the methane production from lignocellulosic materials compared with soluble substrates. Of course, this first order models are sigmoidal shape, and they can actually have three distinctive production phases. In the beginning, you can find lag phase, and then you can have exponential phase, and then plateau, or zero order, basically. Constant values, there is no more biogas produced. The experimental data also can be mathematically described by applying various models, including non-first order, along with some other nonlinear growth models. I'm going to just introduce this selected kinetics, something like exponential, with this kind of equation here. You have here the methane yield, or cumulative methane yield, equal to the final methane yield, which is B0 times 1 to the minus exponential minus KT, and k is the rate constant. And we can use the experimental data to calculate, or to estimate, basically, the B0 and k. For Gompertz, is the same thing. Actually, this kind of form for Gompertz equation, and it has also some b-value, which is the final methane yield, and it has also lag phase. So if you would like to predict the lag phase, you can use this kind of equation. Fitzhugh equation, it's more or less like exponential, except that it has the final term. It has also exponent, which is they call it shape factor, and it is dimensionless. Cone factor, the same thing. Actually, it has also this kind of shape factor, and we can also use the experimental data to calculate, to estimate for Gompertz. We can estimate B0 and RM. This is the maximum methane production rate, and theta is the lag phase, for example. Also, for the other two equations, two models for Fitzhugh or cone, we can estimate B0 and K and N. All of these models, usually you can use actually the time as days or in hours, but for Gompertz, especially if you use this kind of form, the time should be in hours in this case. Here, this is data fitting of cone model. I'm not actually going to go in details how we can get this one. This is just to compare the predicted against the measure. And this is just example again for methane yield of mixture of Spirulina platensis and switchgrass. As you can see, actually, it's good fitting if you compare the measured against the predicted values. Next video, I'm going to use to introduce maybe how to use Excel to estimate the values for the constant and the parameters here for this model for Gompertz equation. This will be the next video, how to use experimental data to estimate B0 and theta and RM for Gompertz equation. With that, I would like to thank you. And here, this is the email for the channel. If you have any question, just email me and I will be glad to answer as soon as I could. Thank you. Bye-bye.